Hello calculus kids, welcome back to another lesson. This is Mr. Bean, and in today's lesson we're going to have an introduction into related rates, which is going to be real nice. We'll spend 2 lessons on related rates. This one's just the introduction to it. Now, to be able to understand related rates, basically how rates relate to each other, you first have to just think about how variables relate to each other. Many times variables have this familiar relationship, things you've seen before. A great example of that is just the Pythagorean theorem. You've seen this over and over again for several years, just how you relate a right triangle and the sides of a right triangle together. Okay, this would be a relationship that we're used to for these variables. But a triangle does not always stay exactly the same. It's not like static or it's not moving. Sometimes it's dynamic and a triangle might be changing. So for example, let me move this triangle around. What if the height was exactly the same? This height up and down stayed the same, but the base of it, if I can make it do it, but maybe the base got longer and longer and longer and longer and longer, like that. So the base was changing of this triangle. Well, that would be a rate of change for the base, although the height might not be changing, but the hypotenuse changed as well as I drag that triangle out. So the rate of change of the base and the rate of change of the hypotenuse are what are called related rates. They both have a distinct rate assigned to that dimension, but they're different, but they do relate to each other. Just like our Pythagorean theorem variables relate to each other, these rates relate to each other. Okay, so that's the gist of a related rate, where you set up an equation with variables, and then when you take their derivative, those derivatives, those rates of change, those are related to each other. Let me show you what I mean by that with this. So when we take the derivative, it's almost always with respect to time. So I'm going to write over here on the side d of dt, because I'm taking the derivative with respect to time. If you think back to our implicit differentiation, remember that where we would take d of dx, but you might have like x squared plus y squared equals 5, something like that. And so you had to take the derivative of a y. Hopefully this is familiar to you with the implicit differentiation. Well, what we're going to be doing here in this lesson has some very strong similarities to that. But instead of respect to x, we're going to do it with respect to time. Almost always. I said here not always, but most of the time it's going to be like that. So let's do that. Let's say that this triangle we have is changing with respect to time. And so we're going to take the derivative. Now the derivative of a squared is just 2a. But then we have to do the derivative of the a. If you remember that, the derivative of just a is dA dt. It's basically a form of the chain rule. You take the derivative of a squared and then the derivative of a with respect to time. Plus, now we do it again, the derivative of b squared is just 2b, and then you have to do the chain rule. The derivative of b is the derivative of b with respect to time. Equals, and then here we have 2c, and yes, you guessed it, dc dt. Okay, so what in the world is all this stuff? This is just showing you that if you had a triangle with the Pythagorean theorem set up, then this tells you right here, this dA dt tells you the rate of change of A, of side length A. This dB dt would tell you the rate of change of side B, and then dC dt would tell you the rate of change of the hypotenuse. That's what these are, and they are all related together in this equation. So they're related rates. Okay, let's put it into practice. Let's do a problem here. We have a police car. It's speeding towards an intersection. Okay, so this police car is going down that way, and the bad guy is taking off in the speeding car, taking off that way, and trying to escape him. So what we're trying to do is set up some type of an equation first that relates these together. So I gave us a really easy one just to stay with a right triangle. In fact, this whole lesson I'm just going to do right triangles just to keep it basic, but your practice will have a lot more than just triangles in it. So we have, what's our relationship here? Let's start labeling some things. I always like to call the thing that's horizontal x, and the up and down thing, the vertical, I like to call it y, because it helps me remember later on what I'm dealing with. Or maybe I might talk about height if I knew it was something that was vertical up and down in the air. Maybe h could work too. And then this hypotenuse, we can call it whatever, c or z, it doesn't really matter. All right, let's set up a relationship. How do these things relate? That is just the Pythagorean theorem. So x squared plus y squared equals z squared. And then what are we trying to do? We set up a relationship. Then we're going to find an equation that shows the related rates of these vehicles with respect to time. So derivative with respect to time. So that's going to give us 2x dx dt plus 2y dy dt. And then that equals 2z dz dt. Now let's think about what this little equation means here. Dx dt represents the rate at which x is changing. So it's the speeding car. It's the guy who's trying to escape. That's the dx dt. And then the dy dt is the police car that he's traveling down. So in fact, if we knew what the number was, that number would be negative because the distance is getting smaller. So the rate of change would be headed towards the intersection point. And then dz dt would represent the rate of change of z. In this case, how far apart in a direct line of sight the police car and the speeding car, how far away they are from each other. So you could tell if he was getting closer or further away by plugging in how fast these vehicles were going. In this example, I didn't give you much of a picture. And that was on purpose because I want you to get used to many times you won't have a picture and you have to come up with a scenario yourself. What I did give you was A, the airplane, and O, the observer. So if you read through this, you can kind of follow along with what I'm doing. We've got an airplane flying horizontally. So it's flying until it goes directly over an observer. So it's going to be going this direction, right? So let's go ahead and draw that it's going to be traveling this way. And yes, it should be a straight line, but I'm using an electronic writing pad and that's really hard. And then this one will be also a straight line up and down. So I've got the vertical distance up and down, the horizontal distance, and then let's do the straight line distance, like how far apart these things are, the airplane from the observer. Okay, so what else do we have going on here? The airplane is maintaining a constant altitude. I'll come back to that. Okay, let's set some things up here. So this would be like my y. This will be my x, the distance that it's traveling towards the observer. And then my straight line of sight, I can just call that z if we want. And let's set this together. How do we put these all together? Pythagorean theorem again, x squared plus y squared equals z squared. And yes, I know all my examples are Pythagorean theorem. You'll have others. This is just to drill home the point of how related rates work. You'll get some practice with other problems. Let's see here. The constant altitude part, this. Constant altitude is important because that means that this thing, this y, that is a constant. So when we have a constant, if you think back, what is the derivative of a constant? The derivative of a constant is 0. So this y squared, when I take the derivative with respect to time, that's nothing. It's going to be a 0. Okay, let's pretend like I forgot about that. Let's just go ahead and take the derivative regular. So 2x, and then I get dx dt plus, now yes, we could put 0, but I'm going to pretend like I forgot that it was a constant, and so I went ahead and wrote 2y dy dt equals 2z, and then that's dz dt. Okay, now this is where we look at dy dt. How is this changing? So dx dt is basically the speed of the airplane. That's this, dx dt, how fast airplane is moving towards the observer. dz dt is how quickly this is getting smaller and smaller and smaller, the distance between the airplane and the observer. dy dt is the altitude, how much it's changing by. And since we know that it's a constant altitude, dy dt does not change. So that whole thing becomes a 0. And that's where we can simplify this down and have our relationship just be 2x dx dt equals 2z dz dt. And yes, you could divide by 2 from both sides if you wanted and clean it up even more. But this is the relationship now between the related rate of the airplane, which is the speed of the airplane, and how quickly the airplane is getting closer to the observer here. Okay, and that's everything for this lesson. So again, you'll have a lot more different types and varying problems. If you get through the practice and you feel like you don't have it, just jump to a corrective assignment on the website and you can try one of those and you'll get some more practice on it. And then on our next lesson, we'll get into related rates, but actually solving them with a bunch of numbers. Today, we're just setting it up, understanding how to set the variables together in a relationship, and then take their derivatives with respect to time to see how their rates relate to each other. All right, rock that mastery check. See you back in the next one.